Okay, good afternoon, everybody. It's my pleasure to open the afternoon time slot. We will have a keynote lecture by Professor Schnitzer from Graz University of Technology. He would discuss with us the low-carbon technologies for the agro-food sector. So let's start, please.
Yeah, thank you. Thank you. It's always a pleasure to be selected as the first speaker after lunch. So the organizers believe that I can keep you awake, yeah? Or I don't disturb you when you have a short nap or something like that. Okay. Yes, welcome this afternoon. I'm Hans Schnitzer. I'm coming from the Graz University of Technology. My background is process engineering, and I mainly work in the field of energy efficiency and use of renewable resources and renewable energy. So what I'm going to tell you and to discuss with you is some findings and some still open problems we made in several projects. So we are working here in the Balkan region, mainly with the National Cleaner Production Center in Macedonia, in Skopje. But we are going to start a new project under the patronage of the UNIDO with Serbia, Albania, Croatia, Montenegro, and Moldova in 2 weeks from now. So there will be more results very soon. We are working with the INTEC, which is a private research institute in Austria, working on renewable energy, mainly on solar energy. But I also work with the university in Ho Chi Minh City in Vietnam on the food industry there, and I've been recently to Cambodia to see some industry there. And I'm working on some European projects and also in the International Energy Agency, Task 33, which is already closed, about solar heat in process industry, and the Task 49, which is also about renewable energy in process industries. So what's the background for our discussion? Well, I don't need to introduce this to you because you are working in this field, and so many other presenters also discussed it. The EU has a key ambition to develop a low-carbon economy. I don't ask you, and please don't ask me, what is a low-carbon economy? I guess nobody knows in detail, but we are discussing it and we are aiming for it. But this is what we'd like, yeah? But anyhow, what we like to is to cut the greenhouse gas emissions by 80% in the next 40 years. And 80% is a lot. Yeah? If you look at it, now we are discussing about 12%, 20% in the next 10 years and so, but 80%. 80% is not an improvement of the existing system. 80% reduction is a change of the system. You cannot improve existing systems by the factor of 5. You have to change. And this is the challenge, and also a challenge for research, for researchers, for industry, for politicians. How can we manage a change instead of managing an improvement? Well, there are other resources where you can find the need for this transition. This is the result of the summit of the G8 in 2009 in Italy. And they said, okay, we support the goal of developed countries reducing emissions of greenhouse gases in aggregate by 80% or more by 2050. So also G8 says we have to reduce the greenhouse gases by 80%. Well, how can we do that? Some countries have set up a low-carbon strategic plan. Well, this is just how I try to show it. We have to go down from 100% in 1990 to 20% in 2050 in the power sector. Should be almost zero greenhouse gas emissions, so completely renewable supply in the power sector. Industry has to go down by the factor of 5 about, transport has to go down by the factor of 3, and agriculture and others have to go down. So this is the challenge. If you look at innovation and market strategies, you find that in general a market penetration follows an S-shaped curve. So these are the early adapters, this is then the main followers, and these are the laggards. And if you look at the targets of the EU, we had the 2012 target, we have the 2020 target, and we have the 2050 target. They are exactly on such an market penetration curve, which shows that we are here. The curve is very flat, so the effort we have to do is very low. So we are early adapters. We are those people who will profit from the process in the long term. Here, the maximum efforts have to be around 2038, 2040, where there is the steepest curve and the highest shape, and then we have to reduce about 4,000 megatons per year. Now we have to only to reduce some 1,000 megatons per year. So this is the challenge, and this is a challenge for changing and not a challenge for improving. Japan, for instance, has set up a low-carbon strategy for the energy supply, for the transportation, for the residential commerce and the industry. But what you see, there is the same need for activities. And in all the sectors, we need to do three things. This is the reduction of the service demand. This is the improvement of the energy intensity and the improvement of the carbon intensity. These are three separated strategies to reduce the greenhouse gas emissions in total. So, if we first discuss reduction of the service demand. So this, if we work with the food industry, how can we discuss the reduction of the food produced? Yeah? But there are several options, but it's not my specific issue, but there is, if we look at the losses, we have to reduce the post-harvest food losses going from the production on the farms to the retailing. So in many countries and many regions of the world, we lose about 100 to 150 to 200 kilograms per year per capita. This is 200 kilograms per year lost from harvest to the food production. Yeah? This has been produced, this is there, this is just lost through bad storage and transportation enterprises. In Europe and in North America, we have a lot of food waste. This is about 100 kilograms per year and person is food wasted, used, which is already produced, is at the retailer shop, but has not been eaten. It's just thrown away before being eaten. Yeah? So this is, of course, a large potential also, because in this food there is all the energy from the agriculture, the energy of the transport, the energy of the production, and maybe of the cooking is included in this. So this is what we can do on the service demand. And then what we has not discussed also here is changing of diet. So if we all switch to vegetarians, this will reduce the emissions quite a lot, but this is not what I would propose out of my personal point of view. While going to the more technical level, if we work with industries, we have two ways to reduce the emissions. One is an improvement in the energy intensity, and the second is the improvement in the carbon intensity. So this is going to be more efficient or more effective, and this is changing the sources of energy from fossil to renewable sources. So if we go into the companies, we say, okay, we have here the supply and the transformation side on the one hand. On the other hand, we have the technologies that are used in the process industry. So with the process industry, with the technologies, we can discuss process integration, efficiency of the electricity requirements, process intensification. While in a region like Austria, it is also the heating of production halls. About 17% of the energy used in industry in Austria, and I guess it's a similar number for the whole EU, is just for heating production halls. Yeah? And they have a very, very poor quality sometimes. Well, and in the supply and transformation, we can use cogeneration processes like cogeneration of heat and power. On the carbon intensity, we can switch between the fossil fuels. We can switch from coal to oil to gas. The process is rather far advanced in Northern Europe, so we have hardly any coal more in industry, except where you use it out of technological reasons, but not for heat. But it may be different in southern countries or in eastern countries. And then, of course, we have to the possibility of switching to renewable resources, where we go on biomass. We will discuss this later on. We go on solar and thermal process industry, and the energetic utilization of waste. And then, of course, the industry can sell waste heat and also can sell electricity. So if we discuss the shift from the fossil sources of energy to renewable sources of energy, we should discuss the energy services. So this shift should not replace coal or oil, but it should provide the energy service needed through a renewable pathway. And so we have to discuss the energy services we needed, which are, well, roughly said, 6 different energy services. One is low temperature heat, up to about 100 to 120 degrees centigrade, which is, of course, room heating and cooking and things like that. Then we have the high temperature heat, which is for steel industry, for cement industry, and maybe glass and bricks and so on. Then we need energy for mobility and transport. Then we need the energy for light and information. Then we need for power and drives, like fridges and elevators and things like that. And then, of course, we need resources for the chemical industry, which is also coming at the moment mainly from the fossil source. So if we look at the possible pathways to go from the solar energy to this energy service, we can select 3 different ones. The first is the direct utilization of the solar radiation. The second is the indirect utilization of solar radiation. And then I take it extra as the photosynthesis. Yeah? So the direct utilization is clear. It is photovoltaic. It's solar thermal systems, and it is a thermal power system, concentrating or draft, whatever this is. Indirect utilization, of course, we have the wind. It's also solar power, but it's not the radiation by itself. It's the hydropower. And there's something like TD, DC, temperature differences and concentration differences. Yeah, you know, there's some research is done on ocean thermal converters using the warmer surface temperature of the oceans with a colder deep temperature. Well, we could use the temperature difference between day and night to everywhere we have a temperature difference, you can run a machine. We could use the concentration difference between the fresh water of the rivers and the seawater, the salt of the river, by osmotic things. So this is not very common at the moment, but there's a lot of things going on. Speaking of photosynthesis, we also distinguish between 3 different approaches. Let's say the first one is agriculture. So where we have short rotation, we harvest every year or several times every year. This is the agriculture part. Then we have the forestry part, where we harvest every 7 to 100 years. And then, of course, we have the bio-waste. And the bio-waste can be post-consumer waste or from industry or from farms or different bio-waste. So this is the first level of distinctions. Then we have geothermal energy, which is not solar, but it's not renewable. Also, the sun is not renewable, yeah? But we call it renewable because it is, in this period of times we are thinking it is renewable. And we have the tide energy, which is, I don't know, lunar energy or something like that. But they also can be used in the term of the renewables. Well, and then from this level we have to come down to the level of the energy services by using energy transfer and storage medium. And I guess electricity is the most important one, and electricity will be more important in future. Everybody wants to switch to electricity. We want electric cars, we want heat pumps for heating, we want more control strategies, so electricity is going to be more and more important. And of course, we can go on this from the biomass, we can go to biofuels, and to bulk and fine chemicals. And there's also, of course, on the horizon, hydrogen technology. I don't know how important it will be, but it is on, we have to discuss it. All the systems Need storage, of course. Big issue in all these conferences. Sun is shining every day somewhere. It's shining all the time, but not only all the time on every place. Wind is blowing everywhere, sometimes nowhere, all the times. So we need the storages. Biomass has the storage included. It's easy to store. Yeah? Electricity is much more complicated to store. And then we have to go down to our services. And now we have different pathways. If we go in the low temperature, we have the passive technologies, which is passive houses, good insulation, and things like that. And the active technologies like solar thermal solar collectors, and then we also included heat pumps because it uses the ambient air, which is also solar energy somehow. So this is the low temperature sector. Then we have the high temperature sector, where we go, of course, with electricity. We can go with hydrogen, and we can go with incineration, like we do now, gas or liquid. But mobility, of course, we can go on biofuels, we can go on electricity, we can go on hydrogen. This is not so clear what will finally be the solution, or how many solutions there will be, and this takes some time, I guess. Light information mainly will be, of course, electricity, but maybe it is a direct utilization. So on a day like today, if it's bright outside, we still use electricity here for the light. Maybe somebody invents something where we can transfer light for 5 meters from outside to inside without... It's on the market, but it's never hardly used. Yeah, yeah, but still, daylighting is something which is very nice and then very efficient. So that's why I included this dash line here. Well, power and drives will mainly be on electricity, maybe on hydrogen and on biofuels, and the chemical industry, of course, will be mainly based on the biomass and on the hydrogen. So these are the routes down, and if we look at this, then we find out that the term low carbon is not a very good term, because this area with biomass is very high carbon. It's carbon intensive. Yeah? So some people say if the EU speaks of low carbon, they speak of nuclear energy. Yeah? And not of biomass and not of renewable. So that's why you have to be very careful when you use the term low carbon technologies. I love nuclear energy, so we have a fusion reactor, a very good one. It works already since millions of years. It's 7 minutes away, or 6 light minutes away, and it's quite good working. And also here we have a little bit of fusion. Yeah? So fusion is not the future, but fusion is that what we can use just at this moment. So this is high carbon, low carbon technology. If you speak about food industry, we are mainly here. Low temperature processes. Food industry usually works below 100 degrees centigrade, sometimes up to 120 to 130. And of course, we need electricity. There are some rules we should follow with the system. One is no flame technologies below 100 degrees centigrade. No fire, no incineration below temperature. We can use waste heat, we can use solar heat, we can heat from cogeneration, but no fire. So no heat without power, no power without use of heat in this area. The second may be also no electricity, no direct electricity at this low temperature. So we are concentrating on low temperatures. So that's one of the reasons why we selected the agro-food sector. Agro-food sector mainly works at low temperatures, where we easily can go with solar energy and with cogeneration energy and things like that. This agro-food sector is based on biomass. Yeah? Nowadays, it's mainly processing biomass to food, but as we know, there is a lot of losses of byproducts of leaves and stems and things on the agro-food sector that can be used for other purposes, like other chemicals, like packaging material, and for energy, of course. The fraction of a plant that is on the table is rather small. If you think about, let's say, sunflowers and the sunflower oil, just try to imagine which percentage of the whole sunflower, which is 3 meters high, is finally on your table. It's less than 1%, or maybe 100%. All the other resources are available on this way. Well, and we also found out that the food industry is not so much working on the energy sector. Energy is not so important, and the people are very good in food production, but they are not very good in energy efficiency. So there are some reasons to go on this. Well, how would such a system look like? We have the agriculture here. We transport it to the food production. We transport it to the wholesale or the retail and to the consumer. If we go on a low carbon or a renewable system, we can use solar energy on all these process steps. Here is, of course, photosynthesis, there's solar process heat, there is electricity from renewables, there's cooling, heating and lighting, and there's also cooling, heating and lighting. And every step we have bio-waste, and we can imagine bio-waste logistic systems where we go on the fermentation with all the fractions that contain sugar or starch. We can go with the oily parts, we can go to the biodiesel. With the wet parts, we can go to the methane production through biogas. And with the dry parts, we can go to incineration, wood chips, pellets, or torrefaction and charcoal production. So this is the challenge. How can we build up such a system? And we need, of course, the distribution system. But this is something we have already now, because the existing system provides also gases, fluids, liquid energy carriers and solid energy carriers. So the system is available. It just has to be changed over to new sources and new source technologies. My friends in Italy, Professor Olgiati, tried to build up such a thing for an area south of Naples, where we have olive farms, vineyards, tomato production, vegetables, citrus fruits, grasslands, and other things like sunflower, rapeseed. Then we have the companies, mainly small companies, SMEs, which is the olive mills, the wineries, the canning industry, the sowing from the forest and the cattle farms. And then we need a number of technologies to build up such a closed system where we recycle the energy through biogas or some other biogas energy carrier, where we also recycle the water, because we can use the water from this process, of course, for irrigation again. Food industry, as I told you, works at rather low levels, drying, washing, and heat treatment is mainly below 100 degrees, pasteurizing and sterilizing maybe over 100. So this is rather low levels, like also some others. So if we look at the industry sector, we try to find out, we have an energy supply system, we have the energy demand system, we have a cooling subsystem, and we have the energy recovery system. And in all these systems we can improve. It is very important to start at the core processes. Never start with the energy supply system. So first look at the core processes, which is, I don't know, a fermentation or something like that, yeah? Then go to the separation processes, then go to the heat exchanger network, and then go to the utilities. You should never start by changing the energy supply without doing the optimization first, yeah? This is well known from process engineering, onion shelling, and so on. You know it, I know. But it's not so obvious. Many companies just okay, we change to biomass heating system, yeah? And then they have a much too big biomass heating system, and the system is inefficient. So this is efficiency first, fuel shift afterwards, yeah? Very, very important if you work with the companies, yeah? Well, typical processes in the process industry are pasteurization, sterilization, biochemical reaction like fermentation, and washing, rinsing, evaporation. So this is a bottle washing machine like you find it in many food processing industries. That's how it looks like, and there are a lot of pipes. We have here warm water, we have hot water, we have very hot water, then we cool it down, and then we have to cool the bottles down, because they are going to the filling machine where they are filled with beer, and the beer has 0 degrees, and if the bottle has 70 degrees, you fill it only once. So we have to cool down the bottle first. Well, this is how it looks like, just a very simple rinse water, 25 degrees, 40 degrees, 60 degrees, 80 degrees, 55 degrees, 35 degrees in the ambient water. So we go up with the temperature and go down with the temperature. Obviously, for every process engineer here, fine, we can do some heat recovery system in this. And we put a scheme with the heat exchangers and the heat pumps and saving more than 50% or something like that. Similar with blanching lines or with a spray dryer for milk. I don't go into detail for that. Well, so from the optimization of the machine, the dryer or the washing machine, we can go to the integration scheme. I guess process intensification in food industry should offer minus 25 to minus 75% in energy consumption. It has been calculated by our colleagues in Delft. What we are working is integration of operations, doing some processes together, like mixing and milling, or mixing and heat transfer, and also very important, switch from batch processes to continuous processes. Food industry mainly has batch processes. It's very, very little continuous processes. And to switch this is also very important. Heat recovery from effluents, of course. Well, we try to do some pinch analysis to bring some heat transfer systems into the processes, which is sometimes complicated if it's batch processes. But this is a production line of a cheese production in Austria. And we see we come in here with pasteurized milk, and we go out with the cheese on this side. No, the cheese, yeah, the cheese is coming out here. But we have also the whey line and so on. And setting up a pinch analysis, we could find that it's possible to recycle or reuse heat from here, and reuse heat from here in this process. This was just against what the people of the solar industry wanted to do, because they're always looking for the lowest temperatures. And we are looking for the lowest temperatures first for the heat integration and the heat recovery, and then for the others. Well, some other approaches: cogeneration of heat and electricity, cogeneration of compressed air and heat, cogeneration of cold and heat, regeneration. Or what they did now in a company in Vienna is a quadrogeneration. They made heat, cold, power, and the CO2 for the juices. Yeah. Okay. So this is, I guess, this is quite well known to most of you how cogeneration works. I don't go into details. Well, this is a process integration we did in a drying process. This was a thermal dryer before, where we have a lot of gas burners here and a lot of waste heat. And it has just been, again, this is a textile dryer. It's just now the humidity is blown off. It's not heated, it's not evaporated. It's just blown off, and it's dry enough for the next process step, which is dyeing or something like that. Well, another cogeneration is to use the off-gases of a gas turbine directly for a dryer, so we don't need a steam cycle and things like that. It's also in a malt kiln, similar things, pasteurizer. Well, now short about solar energy. We can use solar energy in the energy supply system to provide hot water or steam. In the subsystem used to put it directly into the process, and in the cooling system with solar cooling. So we have discussed a lot of possible schemes, like solar collector putting into the hot water cycle, solar collectors putting into the process directly. In the food industry, we have a lot of these low temperature processes, like drying, cleaning, and so on. Some examples, of course: drying process with hot air for coffee, tea, sweet corn, and tobacco. The temperatures are below 100 degrees, between 30 and 80 degrees. Heat carrier is air. This is an example of an Indian dryer. Well, this is a tea dryer in India, just to show you some examples. Coffee with an air collector, air channel, and the hot water storage and the biomass furnace. It looks like that. 5 minutes, okay. Washing processes. Yes, you see there are a number of applications of solar energy. This is a pasteurizing of juice. Even in Austria, when we don't have so much sun, we can have pasteurizing processes on solar energy. And coming back to our cheese production, we have the heat exchange. And then we found that there's still place for solar energy. But now the solar energy is not at the lowest temperature between 8 and 27 degrees, but it's in the range of 36 to 65, where we do not have the potential for heat recovery through the pinch analysis. Last week we opened a solar brewery in Austria, where they have 1,500 square meter solar thermal collectors. They obviously stopped playing football and used this field for a solar thermal collector. I don't know if they play football on the roofs, or if they put the collectors on the roof and play football on the green field. I don't know. Yeah, solar cooling is a discussion, yeah. Very severe discussion between absorption cooling and photovoltaic plus compression cooling. So it's a very, very tough competition, and I'm afraid the compression cooling will win. It's much faster and much cheaper. Okay. Maybe for your information, if you look at these schemes, you can go to the website. We have a website which is called the Zero Emission, and then you can go to the website, and then you find all this energy efficiency for the industries. So let's say food industry, you get some information about the food industry, but then you can go, let's say, a general description, what is sterilization. You see the typical sterilization processes, and then for cooking and pasteurizing in the food industry, you find pasteurizing typical processes, typical temperatures, and you can also find links to the case studies and the experts. So this is something we are building up now in this green food process and European process, and we are also using in the low carbon processes. Potential for solar process heat for Europe, it's about 100 gigawatt hours and about 150 million square meters of solar collectors. Okay. This is from Cambodia, wood to electricity, gasifier with which is biogas, of course, you know. This is from a project in Vietnam. This is how a pineapple looks like before processing and how it looks like after processing. And if you look at all the side streams, you see the pineapple is not growing like a cylinder, and so we have a lot of waste which can be converted. Again, analyze the whole product. This is a nice way of cogeneration. These are greenhouses with photovoltaic on the roof. So this is a cogeneration of electricity with vegetables. So we don't need extra area, but we go on the roof of the system. Okay, biorefineries, I guess there are many papers here about biorefineries, what we can do. We always try to use waste first and then crops. Green biorefinery with excess grass. We have grass. This is the grapeseed from press cake. You see, this is press cake from a winery in Skopje. It's in my hand to see a lot of seeds. Well, there is much oil in it, so you can separate the seeds and use the oil, or you process the whole biomass to fuel. Packaging material, bio-based packaging, fibers, polymers, packaging, and this is made from mushrooms, so this is something we are also working on. Well, finally we have now an existing geocentric system. So we're taking the resources out of the earth and putting them back. So we extract the oil, the coal, and the gas, and the uranium, and we put it back in landfills and carbon storage. And this is the geocentric system. The scientists found out 500 years ago that our system is heliocentric and not geocentric. And this is also what is upcoming here. We are waiting for an upcoming heliocentric system, where all the economy is about solar power, solar energy, solar materials, and that's what we are aiming for. Thank you so much.
So thank you very much for keeping the excellent timing. It's been quite an interesting lecture, prompting for proper discussion. Okay.
Just
Professor Klemes.
quick short points. I'm Jiří Klemes from the University of Pannonia, Hungary. Thank you for a nice presentation. I've got just two short points. One has been inspired by very nice lecture this morning about New Zealand. And to my surprise, New Zealand has got the vast majority of emissions from the agriculture. But not from the agriculture industry, from the livestock. And when I looked on the web to Switzerland, it's quite similar. And this is what we are not always considering. You know, we are people doing this industry, but agriculture has got this livestock part, and it's quite substantial. And it is very much related carbon greenhouse gases, because it's not only carbon, it's also methane, it's also nitrogen. So the second point is, I think we should consider not only emissions, but footprints. As if we are looking on nuclear power station, well, emissions during the time when it's running are minimum. But if we consider footprints, the picture is totally different.
Yeah, we have the non-CO2 agriculture. It is here. Yeah, so it's, I guess it's about, let's say, 10 to 12% of the present emissions. Yeah, this is non-CO2, which is methane and nitrogen oxides and so on. And of course, there's a different approach. It is fertilizer. How much fertilizer and how much energy is already in the fertilizer? How much do you in them?
No, it's about manure.
And then the second is, can we change this by using biogas plants, using the manure in the biogas plant, something like that. But it's also to keeping the soil fertilized, because we also have emissions from the soil. Yeah, and then of course we have a lot of emissions on the agriculture by using diesel. Yeah, and sometimes very, very old tractors, and so not always the highest technology. So also in the transport sector we have agriculture included.
Thank you for your presentation. If you go to the California Futures website, Arnold Schwarzenegger, who was the governor there, pushed through a very strict agenda to follow something very similar to that and reduce their greenhouse gas emissions in the state of California dramatically by 2050. And they are relying a lot on solar as well as being a key component of the reduction. So that's an interesting comparison to your work if you would like to look at that.
Yes. Well, I know this was Europe centralized, what I told you. But there are high activities in New Zealand, for instance. Australia also has a low carbon plan. Some states in the US have, yes, and well, most states in Asia have. But I don't know how strict they are following it up, everybody. So there are more plans and activities on this field, I guess.
All right. Hi, Mark Hollis from the Royal Institute of Technology in Sweden. We've just finished some analysis together with you and Lisa that looks at the potential of biomass systems in greenhouse gas mitigation.
Louder, please.
Greenhouse gas mitigation in different sectors. So one of the interesting things was it's just that space can potentially play an important role when it comes to solar collecting. I mean, just the terrestrial space that's available. Perhaps you have some comments about that in particular.
Yeah.
Just to say, I find the work very interesting because you illustrate that there's a lot of waste from current activities that we could be using a lot better. Thank you.
Okay. Of course, biomass is always competing with food, energy from biomass. And well, in our project, we never use the same space. We use only residue biomass, yeah. And except in this one example with the football place, we go on roof areas with the collectors, solar thermal collectors, and the photovoltaics, because food is much more important than energy. Yeah, absolutely agree. Yeah. But on the agriculture, there's so much biomass. Because if you look at corn, you eat only the seeds, and if you look at, I don't know, sunflowers or something like that, we never use whole part. Yeah.
Professor Dutch.
You try to transfer that knowledge to students, because students learn usually a lot of packages of different knowledge, but we usually don't teach them integration of all this knowledge on this scale, in this way. I think it's a crucial point. Do you do that?
Yep. Well, I'm teaching chemical engineers, and they know about integration a little bit. Yeah, they should know at least. Yes. The question was, what do you mean by students? So, with this low carbon project in the Balkan region, we train experts. Some of them are academics, some are not academics. So it's like, for me, they are also students. So we train in these 6 countries I showed you in the beginning. We are going to train local low carbon experts, and they should go to the companies. They carry out the case studies, and we coach them, and we check their reports on this. On the studies, I'm teaching chemical engineers. They should know about energy. I'm teaching their energy efficiency and including pinch and things like that. But we also have a study which is called Global Studies and Environmental Studies, and they also give a lecture there, but I cannot go into detail. Just tell them, think broad, think on the systemic level, and not only on the technology. But we need new technologies as well.
What about the reliability of this system, this integrated system? Because I saw that you have to have the grid, right? You have the grid and you have this integrated system. So if you don't have the grid, so what's the reliability of this system?
Okay. My colleagues with a biology background, they always say biodiversity gives stability and monocultures is unstable. So that's what we used to say here also. If you have many sources and many networks, it's much more stable than we rely only on oil and gas or nuclear energy. So networks give stability and diversity, biodiversity in energy sources also gives stability, I'm sure. Yeah, but the challenge maybe is storage or demand-side management and all these things. This is not easy. Yeah.
Please, last question.
Yeah, thank you for asking the talk. My name is Joey Yuan. My name is Joey Yuan. I'm from Exeter University in the UK. I saw that you said biomass is high carbon. I just want to comment on that because I think that's not entirely true. You need to consider what sort of biomass.
Yeah. Okay.
And also I have a question. I just want to know what are your views on GM crops?
Okay.
What are your views on genetic modified crops?
Okay. Good. Of course, the idea of low carbon is no low net carbon or no additional carbon or no fossil carbon. Yeah. But wood and biomass has carbon, so it is a. Okay, we should distinguish between carbon in the cycle and carbon in the storage or something like that, I agree. But it's dangerous too. Because the people always say, okay, you have a biomass heating system, there's so much carbon dioxide coming out. So it's not low carbon. GMOs, I think might be okay if you go on the energy side only. But usually we try to avoid them on the food side. But on the other hand, of course, it's if we go on meat more than, I don't know, 10 billion people, it might be necessary. Yeah. But we don't have, I don't remember any of the cases where we had GMOs. Yeah.